Good evening, ladies and gentlemen. My name is David Navasardian from the Public Services Office at JPL. I'd like to thank all of you for coming to the May edition of the Von Karman Lecture Series. Kepler, a NASA mission that launched on March 6, 2009, is a spaceborne telescope designed to survey distant stars to see how common Earth-like planets actually are. The spacecraft will detect planets indirectly using the transit method, which is measuring how a star's light dims slightly as one of its planets passes in front of it. Besides revealing the presence of a planet, this light signature can also tell us the planet's size and orbit. Other measures are then used to determine if each planet discovered is in the habitable zone, that is, the distance from its star where liquid water could exist on the surface of the planet. Tonight's guest grew up in Waukesha, Wisconsin, where dark nighttime skies inspired lifelong interest in astronomy and space exploration. After earning a Bachelor of Science degree at the University of Wisconsin and a PhD at the California Institute of Technology in Pasadena, California, he joined NASA's Jet Propulsion Laboratory, specializing in space telescopes. He was a member of the team that fixed the Hubble Space Telescope's blurred vision in 1993, and later served as a lead engineer for the design of Spitzer Space Telescope and as project manager for the Galaxy Evolution Explorer. The two telescopes launched into space in 2003. He currently serves as a project manager of the Kepler project. Ladies and gentlemen, please join me in welcoming tonight's guest, Dr. Jim Fanson.
Good evening, everyone. I'm very pleased to be able to address you this evening. The Kepler mission, as you just heard, is NASA's first mission capable of discovering Earth-sized planets orbiting other stars in the galaxy in a region that we call the habitable zone. And I'll be talking to you more about what the habitable zone means. This first image shows an artist rendering of the spacecraft, which is not orbiting the Earth. It's in what we call an Earth-trailing solar orbit, drifting behind the Earth, much like the Spitzer Space Telescope has been for the last 5.5 years. And then off in the upper left-hand corner of the image, we're actually looking at a star, seeing a planet orbiting that star and passing across the disk of the star, which is what we call a transit, and that's the method that Kepler uses to find planets, and I'll describe that more in detail to you as well. But first, I want to take a historical perspective, because the Kepler mission, unlike most missions that we launch and fly in NASA, is designed to answer a very old question, the question of whether there are other worlds like the Earth around other stars in the night sky. This question, we know, has been on the minds of humans for thousands of years because we can read the written record of the ancient Greek philosophers. And for example, Epicurus, who lived in the 4th century BC, in one of the letters that he exchanged with his colleagues, speculated about how there have to be infinite worlds both like and unlike this world of ours. We must believe that in all worlds there are living creatures and plants and other things we see in this world. So in some sense, we now, standing upon 100 generations of technological advancement, are privileged to live in a time when we can finally answer this question scientifically once and for all. So this is, in some sense, the closing of a large intellectual arc with our ancestors and colleagues in a very real sense thousands of years ago. I'd like to digress for a minute and give you a little bit of foundation in astronomy, so bear with me if this is all already familiar to you. The universe is populated by galaxies, and this image taken by the Hubble Space Telescope was a 10-day-long integration pointing at the emptiest part of the sky that could be found to point the Hubble telescope at. This picture was taken in 1995. And lo and behold, out of this long time integration, you see this image. And you may think that these are stars across the field, but in fact, these are all individual galaxies, thousands of them. There are only 2 foreground stars in this image from our own galaxy. So galaxies are the building blocks of the universe, and there are many hundreds of millions of galaxies in the sky. Now, interestingly, this image was taken by an instrument on the Hubble telescope that was built right here at JPL called the Wide Field Planetary Camera 2. It was used to correct the blurred vision of the Hubble telescope, and it was installed into the telescope in December of 1993 by astronauts. And it has been the workhorse camera now for over 15 years. And this morning, it was removed by astronauts in the final servicing mission and will be returned to the Earth sometime late next week. And this is a picture taken yesterday during the servicing mission, and you can see in the, if I can find a laser pointer here. Bear with me while I figure out where the laser portion of this is. Does this have a laser? Be careful not to shoot it at me. Well, at any rate, in the center portion of the, and maybe I can do this with the cursor. So let me point my cursor. This rectangular feature here on the outside of the Hubble telescope is the radiator end of the Wide Field Planetary Camera, which is a pie-shaped instrument about the size of a small grand piano that plugs into the side of the telescope. And that is what was removed. And this radiator was used to cool the detectors in the camera by facing very cold space and thereby giving a place for the heat to escape to. And this is something that you'll also see on the Kepler vehicles. This is a common engineering design approach. At any rate, it's just a coincidence that the camera was removed from the Hubble this morning. So moving on with my digression, talking a bit more about galaxies. Galaxies are gravitationally bound collections of stars, typically 100 billion to 300 billion stars. There are probably about 300 billion stars in the Milky Way. And these are engines that are continuously, constantly creating stars out of interstellar clouds of dust and gas. The stars are formed, they're born, they live out their lives, they age and they die. And when stars die, they release their material back into the interstellar medium with heavier elements seeding into the galaxy that were generated in the thermonuclear furnaces in the cores of stars to form later generations of stars and planets. And in fact, everything in the periodic table that's heavier than hydrogen and helium was formed in the interiors of stars. And so everything that makes up the Earth and our bodies and so on was formed in the earlier generations of stars. So these are engines that are constantly creating stars and recirculating, recycling material into stars, and that's what forms planets and planetary systems. And this again is another picture from the Hubble Space Telescope. This is a similar galaxy to our Milky Way, and if we were looking down on the Milky Way, we would be located about here in one of the spiral arms. Now stars, the sun being our closest example, are massive gaseous bodies which shine by means of nuclear fusion reactions going on in their core, converting hydrogen into helium, releasing tremendous amounts of energy in the process. And the life cycle of a star, it turns out, is entirely determined by the mass of the star when it's first formed. Typically, we believe that stars are formed in clusters when something causes a region of space that contains dust and gas to begin to collapse upon itself gravitationally. Condensing out of that cloud will be stars of various masses, various sizes. And the high mass stars are those that burn most luminously. They're the brightest, they're the hottest, and they're also the shortest lived. You get a few, relatively few high mass stars that form in a cluster, and then you get a lot of lower mass stars. You go down through the mass of stars like the sun, and eventually down to lower mass stars that we call M dwarfs, which are much smaller, cooler, and live for a very long period of time. So stars come in a range of sizes, a range of temperatures, and a range of luminosities, the amount of energy that they release. And the life cycle is determined by its mass. So for stars that are the mass of the sun, They will typically live approximately 9 to 10 billion years. Our sun is about 4.5 billion years through its life on this relatively stable region that we call the main sequence, where stars live out most of their lives. You'll notice that the sun is slowly warming as it ages and getting slightly more luminous. And when we talk about the habitable zone, this will be an important thing to bear in mind. At the end of the sun's life, it will turn into a red giant star. Again, it will start to release its material into the interstellar medium that will seed future generations of stars and planets and wind up as a white dwarf ember. So let's now talk about planetary systems and what we mean by the habitable zone. I've shown here depicted our solar system with the sun on the left and the planets ranging from Mercury, Venus, Earth, Mars. In the inner solar system, these are what we call the terrestrial or rocky planets. When you get out beyond the orbit of Mars, you get in the region of the gas giant planets, Jupiter, Saturn, Uranus, and Neptune. And when we get farther out, we get into what we call the trans-Neptunian objects. These are Pluto, Kuiper Belt objects. You can see that Pluto has now been demoted to a dwarf planet status, along with Eris and other objects in that region. Now, in our solar system, we're arranged with the terrestrial planets close to the star and the gas giants farther out. What we're finding in planetary systems around other stars is that this is not necessarily a typical arrangement. It's not necessarily a typical architecture. And so one of the objectives of what we call exoplanet science is to try to understand what kinds of architectures are out there, what kind of planetary systems form around other stars, and Kepler is going to give us a lot of information about that. But let's talk for a moment about the habitable zone. Now, what we're really interested in is finding not ET, but finding ET's home out there in the galaxy. So we're interested in finding places where you could have life living on a planet. And everywhere that we look for life on the Earth, we find that what's necessary to sustain the biochemistry of life is to have liquid water. So we're really interested in starting our search by looking for places where you have liquid water. So we're looking for planets that orbit their stars at a distance that will allow them to have the temperature that is amenable to liquid water on the surface so that you can have oceans. So we're talking about the Goldilocks zone, if you will. If your planet is orbiting too close to the star, it's going to get too hot, the oceans boil away, you're just left with a hot, dead rock. If you're too far away from the star, it's too cold, everything freezes out solid, you don't have liquid water, you can't have biology in the water, and again, you have an ice world. So we're looking for planets that are at just the right range of distances that you can have a temperature that will permit liquid water in the surface, you have oceans, you can have the best chance for the formation of life. Now, obviously, the habitable zone, or the distance where you get that equilibrium temperature, like the temperature of the Earth, depends upon how hot the star is. So if you're orbiting a very massive luminous star, the habitable zone is going to be farther away. If you're orbiting a small, cool red dwarf star, then the habitable zone is going to be closer in. And so this affects how we go about looking for planets. Now, looking again at our solar system, the inner terrestrial planets, Mercury, Venus, Earth, and Mars, these are now shown to scale. The habitable zone in our solar system ranges from about the orbit of Venus out to the orbit of Mars. Now, we know that Venus and Earth are almost identical twins in terms of size and mass. They're very close. And yet, Venus and Earth have taken very different trajectories in their life story. Earth is a water world, and Venus is 500 degrees C at the surface. So obviously something has happened on Venus. We know that the atmosphere is thick carbon dioxide. The pressure on the surface is like sitting at the bottom of the ocean here on Earth. And we also know, of course, that Venus is closer to the sun and it's in a warmer environment. However, you saw in the earlier plot how the sun is slowly growing more luminous as it ages. There may well have been a time in the past, earlier in the life of the solar system, where the situation on Venus was more amenable, and it might in fact have been much more habitable than it is today. The other factor that we are keeping in mind is that we're really interested in looking for planets that range from about a half of the mass of the Earth to about 10 times the mass of the Earth, what we would call a super-Earth. And the reason for this is that if the mass of the planet is less than a half of the mass of the Earth, to take Mars, for example, Mars is orbiting in the habitable zone around our star. However, its mass is much lower than half the Earth mass, so it doesn't have enough gravity to hold on to an atmosphere. The atmosphere on Mars is very thin, and as a result, it's not able to retain the heat that's necessary to have liquid oceans on the surface at this time. We know from the Mars exploration rovers that there was water flowing on Mars at one time in the past, but by now the atmosphere has been blown away, and it's largely a frozen world. There may still be water beneath the surface, but nothing apparently running readily on the surface. So we're looking for planets that have a mass that's above about half a mass of the Earth and about 10 Earth masses. It turns out if you get to be about 10 times the mass of the Earth, the gravity is so strong that you retain the hydrogen and helium gas that was in the protoplanetary disk out of which the planets originally formed. And it will continue to accumulate mass until the mass supply is exhausted. So what tends to happen is it tends to continue growing and become a giant planet like Jupiter or Saturn or Uranus or Neptune. So again, this is a selection process. We're looking for planets that have solid surfaces you can walk on, that have a range of masses and a range of distances from their star. So I'd like to talk for a moment about the person that Kepler is named after. That's Johannes Kepler, who lived between 1571 and 1630. He was a German astronomer and a really remarkable individual. We know him today most famously for the laws of planetary motion, which bear his name. These are the 3 laws that you learn about in the textbook. But what's interesting to me is that he was really a very towering figure in his day, contemporary of Galileo. Kepler coined the term satellite in a paper that he wrote following up on the moons of Jupiter that had first been seen by Galileo. He did a lot to develop the methods of optical analysis of optics that we use today. And interestingly, he used his newly developed laws of motion to successfully predict in the 1631 transits of Mercury and Venus across our sun's disk. But notice he didn't live long enough to witness these transits, but he was the first to make a detailed, precise prediction. And transits, as I mentioned at the beginning, is the method that the Kepler spacecraft will use to find planets around other stars. So the transit method is easy to visualize. You can imagine a planet orbiting a star, as in the image in the upper right-hand corner, and occasionally the orbital plane of that planet will be oriented in such a way that when the planet passes in front of the star, it passes exactly between the star and our line of sight here on the Earth. And when it passes across the disk of the star, because the planet is cold and the star is bright, the planet blocks a small part of the star's light for the period of time that it takes to transit or cross the disk of the star. And that's typically a few hours. So if we are measuring the brightness of the star, we can look for these very slight dimmings that occur when a planet passes in front. And in fact, for giant planets, this signature is quite sizable. If you were looking from outside our solar system back at the sun, and you were lined up in what we call the ecliptic plane, the plane of where the planets orbit, and you were to watch Jupiter pass across our sun, it would reduce the brightness of the star by about 1%. Now, 1% is a sizable signal. You could probably measure that from your backyard with an amateur telescope with a carefully built light measuring device on the back of the telescope. So in terms of finding giant planets, we've actually started to find giant planets in transit surveys on the ground from the surface of the Earth. However, the difficulty comes in when you start looking for planets that are the size of Earth or Venus. In this case, you're only going to see the star dim by about 1 part in 10,000. And the exact calculation for an Earth-sized planet around a Sun-like star is about 84 parts per million. Now that's a very tiny signal, and that's really beyond anything you can measure on the ground, and that's what drives Kepler to be a space mission, to get above the atmosphere to be able to make these measurements. Let me back up here for a moment. Now we have a web page at JPL that you can find at Planet Quest if you go to the JPL web page. And it lists all the known planets orbiting other stars in the galaxy. And right now there are about 350. There's about a planet being discovered every week or every couple of days, so the number keeps going up. And there's a catalog of them, which you see here, on a part of which you see on the right-hand side. But of these 350 planets that have been discovered by ground-based methods, they're found by a different technique. They're found by a technique called radial velocity, where you look at the star's light and you look at the spectrum of the star and you measure where those spectral lines occur. And if you measure carefully enough, you can see a slow backward or side-by-side shifting in the spectrum that is due to the reflex motion of the star being tugged back and forth along our line of sight by an unseen planetary companion. And they've made these instruments sensitive enough now that they can measure the velocity of the star down to 1 meter per second, which is about the rate at which you walk down the sidewalk. And by that method, over time, you can determine that there are planets orbiting the star. Now that method is most sensitive to giant planets and planets that are in very short period orbits that orbit very quickly, that cause the star to move back and forth quickly. And so as a result, most of the planets that we know about are giant planets in very short period orbits, what we call roasters. They're close to the star, they're hot. They're not like our solar system. We don't have any giant planets that are close to the star, but we're finding a lot of them out there. None of them are habitable, and very few of them are terrestrial, that is, rocky. Now, one interesting system is the Gliese 581 system. There have been 4 terrestrial planets found around this star, the most recent of which, Gliese 581d, was discovered last month. And it is the smallest planet that has been found. It's 1.9 times the mass of the Earth. However, the reason that we've been able to detect this planet from the ground is because it's not orbiting a star like our sun. It's orbiting a very low-mass star, a red dwarf star. And it orbits around that star once every 67 days. So plotted here around the star, this is the orbital distance of Mercury in our solar system, and here's the orbit of Gliese 581e. So it's not in the habitable zone. None of these 4 planets are believed to be in the habitable zone. But we're getting to the point where we can start to detect terrestrial planets from the ground, but we cannot find terrestrial planets that are in the habitable zone around stars like the sun. The best we're going to be able to do is to find these kinds of planets around red dwarf stars. So if you're interested in finding planets like the Earth, orbiting stars like the sun, you've got to go to space, and that's what Kepler is all about. Kepler is designed specifically to find Earth-like planets orbiting stars like the sun. So here again is the artist rendering of the Kepler spacecraft, and it's a conventional design. The cylindrical portion here is the instrument, what we call a photometer, because it's measuring the brightness of stars. It's electrically powered. We have a wraparound solar panel that collects sunlight and converts it to electricity. And at the bottom is what we call a spacecraft bus. It's the spacecraft that provides all of the usual engineering functions, pointing control, telemetry with the Earth, telecom with the Earth. It provides power regulation. It processes the data, sends commands to the instrument. And then, interestingly, compared to the image I showed you of the Hubble Space Telescope, this is an externally mounted radiator, again, that is used to reject heat from the focal plane of the camera to keep the focal plane cold. So again, a recurring engineering design approach. This is a section view through the instrument, or through the photometer. Now, one thing you're going to discover about the mission, the Kepler mission, is that we need a very wide field of view because we want to be measuring a very large number of stars simultaneously. We want to measure the light from more than 100,000 stars simultaneously. So we need to take in a large piece of the sky, and so we need a different kind of telescope than what we're used to building and flying. If you think of the Hubble Space Telescope, the field of view on the sky from the Hubble Space Telescope is equivalent to holding a grain of sand out at arm's length on the sky. That's how much of the sky that you get with Hubble. With Kepler, we get a piece of the sky that's equivalent to 2 scoops out of the Big Dipper. So it's 100 square degrees. So to take in that much sky, we need a different kind of optical system called a Schmidt camera or a Schmidt telescope. And in a Schmidt telescope, the light enters, in this case from the right-hand side, it passes through a lens. This lens in Kepler is 1 meter in diameter, and it's made out of fused silica. I think it's the biggest lens that's ever been flown in space. The light then passes to the back of the telescope, reflects off the primary mirror, which is 1.4 meters in diameter, and then focuses on the camera, which is supported in the center, suspended on 4 arms, what we call spider legs in the trade. And then there's the focal plane array where the image is formed and where we measure the light from the stars. This is a photograph of the camera at the prime focus out there in the center of the telescope. It's a 95 megapixel CCD camera. So if you think about your one-shot camera that you buy at the electronics store, the CCD detector in your one-shot camera is about the size of your fingernail. On Kepler, this blue curved surface here is the array of CCDs. It's about a foot square, a square foot of silicon. So it's vastly larger than anything that you've got at home. And behind the focal plane, and you can see in this image how curved it is, and that's because the Schmidt telescope forms a curved focal surface. Behind it is all of the electronics and thermal control system that keeps the surface of the focal plane, the CCDs, at minus 85 degrees C, and the electronics behind it are running at room temperature. This cubic foot of spaceflight hardware contains more than 20,000 components. So it's one of the most complex cubic feet of spaceflight hardware that's ever been built and assembled. You'll notice in the 4 corners are smaller blue squares. These are the small CCDs that are used as fine guidance sensors to stabilize the pointing of the telescope. We actually have pointing stability on this telescope that's very similar to the performance on the Hubble Space Telescope. And that's because we're trying to make very precise measurements of the brightness of stars, and we need everything to be very stable, including we need the image on the focal surface to remain very stable and not move around. These are photographs of the spacecraft in final assembly in a clean room. This was assembled out in Boulder, Colorado by Ball Corporation. And you can see the photometer is the cylindrical section. It has a large oval-shaped cover over the front of it to keep dust out, contamination out, and also to protect it from sunlight after we launch it so that we can do dark calibration. Then we release the cover. You can also see the solar panel that wraps around the vehicle, and you can see the high-gain antenna down here that we use to communicate with the Earth. I mentioned that we needed a very large field of view because what we're really trying to do is not just find one planet like the Earth. We want to know how frequently do planets like the Earth form around stars in the galaxy. So we're taking a census, if you will. So we need to look at a very large number of stars to make that census. I also mentioned to you that we can only see transits when the orbital plane of a planet happens to line up along our line of sight. Well, most of the time, because planetary orbits are randomly oriented, that's not going to happen. So it's only about 0.5% of the time to 1% of the time is a planetary system going to be lined up so that we can see transits. So we need to look at a very large number of stars because only a small fraction of them are going to be aligned appropriately. So our objective is to start out with more than 100,000 stars. We're going to start out with about 156,000 stars. But as the mission progresses, we may find that some stars are not suitable for finding planets. They might be too noisy and too variable. We expect to settle down to about 100,000 for the duration of the mission. So here's the field of view. You saw in the photograph of the camera an array of CCDs, rectangular-shaped CCDs. What we've done here is we've projected on the sky where those CCDs are going to be imaging. And in this left-hand image, this is a picture taken with a wide-angle lens of the night sky, and it shows the Milky Way galaxy. We live in this pancake-shaped disk of galaxy, and in the lower right-hand corner here is the center of the galaxy, and then it gets thinner as you go out towards the edge. And here are some familiar summertime constellations. This is Cygnus the Swan, or the Northern Cross in the summer sky. And this is Lyra with the star Vega. And the field of view that we've selected is just north of the galactic plane, tucked under the wing of Cygnus, in between Cygnus and Lyra. And here on a star chart, we've blown it up a little bit larger so you can see where the actual field of view is. So anytime during the summertime in the northern hemisphere, you can go out at night, you can look straight up into the sky, and you can see where we are staring and continuously monitoring the brightness of stars, waiting for stars to wink at us when planets pass in front of them. Now, one feature of the design is that there are gaps between the CCD modules, and part of the reason we've done that is because there are a few very bright stars in this region, and we don't want extremely bright stars falling on the focal plane because they will saturate the detectors and create other difficulties. And so we've cleverly arranged this layout so that these bright stars fall in between the modules and they don't affect our measurements. So in this field of view, which is 10 degrees by 10 degrees in size, there are about 4.5 million stars that fall on our field of view. I mentioned to you that we're a different kind of telescope than Hubble. I did the calculation the other day, and our field of view, or the amount of sky that we image at any given moment, is about 35,000 times larger than the Hubble Space Telescope. So it's a different kind of machine because we're doing a different kind of science. Now here's an artist rendering by John Lomberg, who was commissioned by the Smithsonian to paint a rendering of the Milky Way galaxy that was faithful to the way we believe the galaxy is arranged. And the painting places the sun at the very center of the image. You can see the sun here. And we live in what's called the Orion Spur, which is a part of the spiral arm, the Sagittarius spiral arm that sticks out here toward the Perseus spiral arm. And the region of the galaxy that Kepler is going to be searching is represented by this 10-degree wide cone of yellow that is just north of the galactic plane. And a typical distance for a target star in our target list is about 3,000 light years. For some of the very brightest stars, we're going to see those all the way across to the other side of the galaxy. For very dim stars, they're going to be closer to us, but a typical distance is about 3,000 light years. So you might ask, how did we select this specific region of the sky? And that's an excellent question. So if we're interested in surveying a large number of stars, obviously you want to pick a part of the sky that's got a lot of stars in it, that's dense with stars. But we don't want it to be too crowded with stars because we want to be able to measure individual stars, and if it's too crowded, the stars are going to get confused with each other. So this means that you want to be imaging near the galactic plane where the sky is dense with stars. We also are interested in having an uninterrupted continuous viewing area because we don't know when the transits are going to occur, and we need to see at least 3 transits to be able to determine that we're actually looking at an orbiting planet. And the reason for that is that there are going to be 10 times as many false positive signatures than there are true planetary transits. So we need to be able to sort out the many false detections from positive detections. So with 3 transits, we get 2 orbital period measurements between the first and second and between the second and third. And if we're looking at an orbiting planet, those 2 orbital periods should match to very high precision. So that's one way that we're going to throw out things, for example, like star spots that might be forming and changing on the surface of the star, and other effects. So we need at least 3 transits, and you get only 1 transit per orbit. So if you're looking for a planet like Earth that's orbiting at a distance like Earth is orbiting from its star, it takes the Earth a year to go around. So you're only going to get 1 transit per year. So if you want at least 3 transits, you got to be observing for about 3 years. And so the baseline mission design for Kepler is 3.5 years. So we want to stare continuously at a region, continuously monitoring the brightness of these stars for a long period of time. So that means that we want a region which is out of the ecliptic plane, because as we go from month to month, we don't want our part of the time to be too close to the sun, where the sun is interfering with our observation. So we want to get out of the ecliptic plane so that the sun never becomes an issue with our viewing. So if you look at a star chart, and this is one, the blue is the plane of the galaxy, and it has this crazy shape because we're taking something spherical and plotting it on a flat sheet of paper. And the green line here is the ecliptic plane. That's the plane that the sun follows around the sky. So you want to be out of the ecliptic, but in the galactic plane. So you've got a good region in the northern sky, and you've got a possible region in the southern sky. And so we could have picked a region in either of these places. We chose to pick a region in the northern sky because an important part of our process for eliminating these false positive detections is to do follow-up observations by ground-based telescopes. And there are more large telescopes in the northern hemisphere than there are in the southern hemisphere. So we picked the northern sky. So that's how we arrived at this particular optimal location. Okay, I mentioned to you that we are not orbiting the Earth. And part of the reason for that is we want to get the Earth out of the way, so we have this continuous viewing zone. Getting away from the Earth also gives us a very stable thermal environment, which is important to be able to maintain the precision of the measurements that we're making. So this is a plot that is looking down on the ecliptic plane, is looking down on the orbit of the Earth with the sun at the center. And the blue circle is the orbit of the Earth around the sun. And this blue dot is where the Earth was on March 5th. We actually launched on March 6th for reasons we can talk about. And we kicked the spacecraft into an orbit where it drifts behind the Earth. So 1 year after launch, the Kepler spacecraft will be at this location. 2 years later, it'll have drifted to this location, 3 years and 4 years and so on. So Kepler is following the green circle, so it has a slightly longer orbital period, so it drifts over time farther and farther behind the Earth. So we show here the spacecraft looking at this particular part of the sky, but remember that the spacecraft is solar powered, so we need to keep the solar panel pointed at the sun. So once a quarter, every 3 months, we do a 90-degree rotation of the vehicle and keep the solar array pointed at the sun as we go around in this orbit. And so what that does is every 3 months, it causes all of the target stars to now fall on a different part of the focal plane. And so we need to take that into account as we read out the data and as we process the data on the ground. Now, to get the data down to the ground and to process the data, to find the planets and to archive the data, we have a number of institutions and facilities that are involved. I'll start here at the NASA Ames Research Center. The Ames Research Center is the home institution of the principal investigator, Bill Barucki, who thought up this idea, and he has spent the last 25 years working on this mission, trying to convince people that it could be done. He is a case study in perseverance, being important in life. I think he proposed this mission 5 or 6 times, and each time he would propose it, his colleagues would read the proposal and say, this measurement can't be made. You're trying to make a measurement that's too precise. So we're not going to select your mission, but we're going to give you a little bit of money to go into the laboratory, and we want you to go prove this or that or that. And over time, Bill and his team were able to convince people, his colleagues, that in fact the measurement could be made. It was difficult, but it was possible. And eventually the mission was selected to be developed by NASA and flown. So those of you younger people in the audience, perseverance is important. The Ames Research Center, which is in Silicon Valley in Northern California, is also the location of the Science Operations Center, where the data is going to be reduced and where the discoveries are going to be made. We then must operate the spacecraft, and the mission operations is being conducted out of the University of Colorado in Boulder, Colorado, and it's actually being used as a training experience for students. They put professionals next to students on console, and I'll show you a photograph of this in a moment, and send commands to the vehicle and get the data down. So it's an opportunity for people to learn how to operate spacecraft. So we're a training facility. And then the manufacturer of the spacecraft was Ball Corporation, and they're just down the street from the Laboratory for Astronomy and Space Physics, or I'm sorry, Laboratory for Atmospheric and Space Physics. So in Boulder, Colorado is where they're doing the engineering, monitoring, and the commanding of the vehicle. Then the data is going to be archived at the Space Telescope Science Institute in Baltimore, Maryland. And they also do some of the processing in what we call the pipeline of running the data through software on the ground. And then finally, coming home here to Pasadena JPL, we are providing the management function during development, and we also provide communication services through our Deep Space Network. And we have, as you probably know, large ground-based antennas in Goldstone, out here in the Mojave Desert by Fort Irwin, in Canberra, Australia, and in Madrid, Spain. And we also are using a modified Australian scientific or science array radio science telescope to be able to receive data from Kepler as well. And in addition, JPL provides navigation so that we always know where the spacecraft is, so it knows how to find the Earth and we don't wind up lost in space. Kepler launched on a Delta II rocket. This is a 3-stage rocket in our case, and the Delta II is probably the most reliable rocket in the inventory. They've had many consecutive successful launches. It's shown in a schematic view to the left. This is the first stage with some solid rocket motor strap-ons that ignite during the early powered flight. There's the second stage, which is the brains of the rocket, and propelled the rocket or the spacecraft out over the Atlantic Ocean. The engine shut down for an extended period of time. It then reignited just as it was leaving the Indian Ocean over Australia. And then there's a third stage, which is spun up on a turntable, like the old record players used to be, and spin stabilized, separated, and then a solid rocket fires and puts the spacecraft on its final trajectory. It then despins and separates the spacecraft, and then we're on our own. Our particular version of the rocket had what's called a stretched fairing, which is the largest fairing that they fly. And on the right-hand side, you can see a photograph. This is the fairing coming all the way around. This is the top of the second stage, and here's the third stage of the rocket. So from this plane upward is the Kepler spacecraft. So again, you can see the high-gain antenna, the solar panel. This is the top of the photometer. So we essentially filled the entire fairing, and it was a tense moment when they're moving these very large, very heavy fairing components very close by your spacecraft in encapsulating and closing out prior to launch. And you can see people down below for scale. We launched on the evening of March 6th. It was a beautiful cloudless night, perfect visibility. If you were standing on the launch pad, this is the view you would see. It's not the place you want to be for a launch. The safest place is out at Jetty Park. This is a nice photograph taken by Ben Cooper of the launch, and you can see the rocket heading up, and it looks like it's coming down, but that's because it's getting so far downrange, it's beginning to fall down toward the horizon. And for people like me who were involved in the countdown, we were stuck in the Mission Director Center, so we didn't actually see the launch except on TV, but we could hear the building rattle from all the noise. So here's another plot that shows the trajectory of the spacecraft. This is looking down again on the orbital plane of the Earth. So here's the Earth at time 0. This is the orbit of the Moon, and these tick marks are one-day intervals. So this was the location of the Moon when we launched on March 6th. This is 1 day later, 2 days later, and here comes Kepler 1 day later, 2 days later. So we flew right past the Moon on our way out of the Earth-Moon system, and this is the trajectory that we took outward. So we're drifting from the Earth now at the rate of about 1 kilometer per second, and we're about 6.5 million kilometers away, still reasonably close by, but moving outward. I mentioned we're controlling the spacecraft from Boulder. These are some photographs of the operations team. After we launched, it took us about 60 days to commission the vehicle, that is, check out all of its systems. We had to make sure that all the spacecraft systems were working. We then had to release the cover from in front of the photometer and let light into the telescope. We had to take our first light image, fine-tune the focus to get the best possible performance, and then take a bunch of calibration data to characterize the electronics and to fine-tune everything that we need to do for the planet search, and then load up to the spacecraft the coordinates of all the target stars and start the search. And that was accomplished just a few days ago. This is the first light image taken by Kepler, and again you can see the mosaic pattern of the various CCDs. This is just a portion of the image, and it's a little bit hard to see in this projection what the image looks like. So I have an enlargement on the easel over here on the stage. You can come up afterwards and have a closer look. There are, as I mentioned, 4.5 million stars in this field, and we had to survey the location of all the stars, characterize the stars. So the science team spent 5 long years making millions of observations from the ground, characterizing every star in the field and trying to figure out what type of star it is, what the diameter of the star is, what the distance of the star is, and sorting out dwarf stars like our sun from giant stars, which we're really not so interested in looking for planets around. There are 3 known transiting planets in the field of view of Kepler. One of them is located here. It's called Trace 2. And we expect to be able to confirm that we can see those transiting planets very quickly within the first few months. We also have some interesting objects that are familiar to amateur astronomers. Here's NGC 6791. Here's another star cluster. To give you an idea of the scale, this red line here is the part of the image that I'm showing you on this page. And I've plotted to scale here the size of the full moon. So again, this gives you an idea of how much of the sky we're taking in. It's a close-up image of NGC 6791, about 13,000 light years from the Earth. And here's a close-up view of Trace 2, one of the known transiting planets. So blowing this up a little bit, giving you a little bit closer look at what falls on each CCD. Each of these rectangular panels here is a charge-coupled device, and there are about 2,400 target stars. Ultimately, we're going to start out with a bit more than that, falling on each one of these CCDs. Now you can ask, what are we going to find? Well, partly we don't know how to answer that question because we haven't been able to find the kinds of planets that we're interested in finding with Kepler. Kepler's going to be the first time we get a look at how frequently do terrestrial planets form around stars. But we can make some assumptions about what planetary systems are like, and we can make some estimates of what we might find. Either way, whether we find lots of planets like the Earth or whether we don't find any, either way the result is going to be a profound result. I mentioned we're interested in doing a census of planets. So we're looking at a large number of stars. So whatever we do discover or determine, we'll be able to say with very good statistical confidence. So if planets are common, planets like the Earth are common, we expect to find many of them. But if planets like the Earth are rare, if we don't find any of them, we'll be able to say with very high confidence that the likelihood of there being planets like Earth in the galaxy is very low, and we are probably alone in the galaxy. But you can play some numbers games and make some assumptions about what is out there. So here's a calculation done by the principal investigator, and it's plotted as a function of spectral type of star. I told you stars come in different sizes, different temperatures, and they're given obvious names like F7 and G2 and G7, depending on their type. Now, our star is a G2 type star. So these are stars like the Sun, and these are stars that are less massive than the Sun. And what is plotted here in different colors are the number of stars or the number of planets that can be found depending upon their size. So dark blue are Mars-sized planets, much smaller than the Earth. In this teal blue color are Earth-sized planets. Then in yellow are 1.3 times Earth size and twice Earth size. So if every star has a terrestrial planet in the habitable zone, then after 3.5 years, these are the numbers of planets that we would expect Kepler to be detecting. So you can see here plotted on the scale, in 60 planets around G7s, 35 planets or so around G2s. So we should detect more than 100 terrestrial planets in the habitable zone. If you do a calculation for outside of the habitable zone, that is closer to the star, farther from the star, we'll get even larger numbers. And then if you throw in giant planets like Jupiter, Saturn, Neptune, Uranus, we expect to find many thousands of giant planets. So again, we're going to find out how frequently planets like Earth are forming around stars in the galaxy and how many of those are orbiting in the habitable zone. Now, I'm an optimist. I grew up watching Star Trek. I want to believe that there are places to go, but we don't have any data, so I can't prove to you that there are places to go. So by the time Kepler is finished, we're going to know whether there can be a Star Trek in our future or whether there's just no place to go. And here's my final slide. The planet search actually began at 5:01 p.m. Pacific time, Tuesday evening, this week. And the first data will come down from the vehicle on June 18th. And that data will then flow into the science pipeline, and we're going to start to see what kinds of things we discover. I would expect that within the first few months, we'll be able to make announcements that we can confirm that we can see the planets we know are out there, the 3 transiting planets. And in the course of the months and years to come, we'll be announcing the discovery first of giant planets in very fast orbits, and then smaller sized planets further out. And after a couple of years, 3 years, we should be able to announce the discovery of planets like the Earth. So with that, I'd be happy to take any of your questions. Thank you very much. Right here, yes, sir. And then we'll go to this side.
In terms of your camera and your aiming accuracy, how many pixels per star that you're looking at?
Well, we have, on average, about 5 by 5 to 6 by 6 pixels around each star. Now, those of you who are familiar with charge-coupled devices know that there's a finite number of electrons that you can put into a pixel on a CCD before it starts to spill over and create mischief on the detector. The full well on our charge-coupled devices is about 1.2 million photons or photoelectrons. So we don't actually want to concentrate the light too tightly, or we're going to wind up saturating the CCDs. And so we sample the image very, very finely sampled so that we distribute the light from stars around 5 by 5 or 6 by 6 pixels, depending upon where you are on the focal plane. Does that answer your question? Excellent. I think we had a question over here. Yes, sir.
How does the data rate between the satellite and Earth compare to, say, home DSL?
let's see, you're going to ask me what our downlink rate is. I believe our downlink rate, gosh, you have to correct me, I think it's about 12 megabits per second. Now, what we do is we stare at this region of the sky and we collect data. We read out the focal plane every 6 seconds. So every 6 seconds we make a measurement. And then on board we co-add all those 6-second integrations to the equivalent of about a 30-minute integration. And then for the pixels around our target stars, we store that data on onboard memory. And we do that for a month. After a month, we turn the vehicle and point the high-gain antenna at the Earth, and we downlink the data. So it takes about a day to downlink the data to the Deep Space Network. And after that, we repoint the telescope toward the target region and resume observations. So we're going to be in a cadence where we communicate with the vehicle a couple of times a week just for health monitoring. And once a month, we'll get a big slug of data down from the telescope and it'll enter the pipeline. So that's kind of the rhythm of the mission. Yes, sir, in the front row.
In case maintenance will be needed, is there any plan or any way that we can reach that telescope while it's far away from the Earth?
Well, we have no plans to service this telescope by astronauts. As I mentioned, we're in an Earth-trailing solar orbit, so we're already 6.5 million kilometers away. If there's a future generation of manned vehicle that can go out that far, in principle, you could journey out there. However, we've not designed the vehicle to be serviceable. So we have no expectation. We do, however, realize that after decades, when the spacecraft goes all the way around the sun and comes back toward the Earth, we may have developed a capability to retrieve it and put it down in the Smithsonian. And so we have a plaque on the spacecraft so that future generations of astronauts can recover this vehicle and get the plaque back, and it'll make a nice display. Yes, sir.
On your camera array, how do you identify the pixels that have gone bad?
We map them. So we do once a quarter, we'll bring down a complete image like this one is printed out and put on the easel here. And we have a lot of diagnostic measurements on the CCDs to see which pixels are going bad from radiation or becoming so-called hot pixels, and we'll map those out. So there's a lot of calibration involved in maintaining the photometric accuracy of the measurements. Yes, sir.
I think you said you turn the telescope toward Earth once a month.
That's
Why don't
right.
you have the downlink pointing toward Earth all the time?
Well, we originally started out with a high-gain antenna that was on a gimbaled arm so that we could always keep the antenna pointed at the Earth. But these missions are implemented with budgets that you're expected to meet. And along the way, you inevitably encounter technical challenges. And we encountered a technical challenge with the company that was building the actuators for the gimbaled arm. And we concluded that we were at a very large cost-risk exposure if we continued down that path. So in order to de-scope something out and save cost, keep us within the budget, we de-scoped the gimbaled antenna. And the price we paid by hard mounting the antenna is that now we have to reorient the vehicle and interrupt our data acquisition. So we have developed careful error budgets, and we have allocated time for the downlinks. So we pay a small science penalty, but we deem that to be an acceptable price to pay to keep the cost from growing. Yes, sir, in blue here.
Well, if you have to reorient to once a month like that, then and you said you're trying to measure to 1 part in 10,000 or something like that. So you have to get back to where you were pointed before, so that each pixel is exactly relative to that star as it was before.
That's right. When we reorient the vehicle and downlink the data and then go back on target, we need to put the image precisely back where it was on the focal plane. And we have the ability to do that within a very, very tiny fraction of a pixel. That's a good observation. So, keeping everything very precisely stable is key to making this observation. And I mentioned that when an Earth-sized planet passes in front of a sun-like star, you get a dimming of brightness of about 84 parts per million. We actually have built the instrument to be sensitive enough to make a measurement at 20 parts per million. And that's a very precise measurement. Now, there are a lot of things we learn from these transits. If we know the diameter of the star, which we can measure by the oscillations of the star, then by measuring the dimming, the depth of the dimming, the depth of the transit, we can determine the diameter of the planet. For the amount of time it takes to cross the star, we can determine how fast the planet is moving, and we can figure out what kind of orbit it is. And using Kepler's second law, that tells us what and knowing the mass of the star, that tells us what the orbital diameter is, and that tells us what the distance of the planet is from the star and what the equilibrium temperature is. So there's just a wealth of data that we can collect from the transits that we'll measure from Kepler. I don't know how long we can keep going here with questions, but go ahead, sir.
Are there instruments on Kepler to determine what kind of atmosphere the planets would have?
No, that's determining what kind of atmospheres may exist around planets is for different missions. So it turns out that the Spitzer Space Telescope and the Hubble Space Telescope have already begun to measure the characteristics of atmospheres around transiting planets. They've done it so far for giant planets. And so we expect that we're going to generate a whole catalog of transiting planets that Spitzer, Hubble, and the James Webb Space Telescope that comes later will be able to follow up on. And I think we're going to learn a lot about these planets from follow-up observations. Yes, sir.
Since the orbit is not necessarily straight on, and so it's not necessarily going to be right across the center of the star, so if it's nearer the edge, it's going to go across a shorter part of the orbit. So how do you know what speed it's going versus what angle it's at?
Yes, you're making the point that you can have different transits across different parts of the star. It turns out that the transits across different parts of the stars have different shapes to them because of the angle that you're coming across the limb of the star. So in addition to the normal measurements that we make, what we call the long cadence measurement, we also have a number of targets that we can select and change from month to month to give us 1-minute measurements. So when we find a transiting planet, we have the ability to say, all right, we now have 2 transits, we know what the orbital period is. So for the 3rd transit, we can predict what's going to happen. We're going to make that a short cadence target. We're going to get very fine time resolution and look at the shape of the transit. And we'll be able to tell things like that. In addition, we have a whole follow-up observing program on the ground that will begin to measure the radial velocity of the star to give us more information about the planet. So there's a lot of things that we can learn. We can't arrive at perfect knowledge of what's going on, but we can get a good idea of what's happening. Yes, in the back.
You said that it's a 3-year time period to take these measurements. At the end of that, assuming the spacecraft is still functional, will you continue to look at the same part of the sky, or would you redirect it to another part of the sky?
Well, that's a good question. The question is, if we go beyond 3.5 years, do we continue to monitor this same field of stars, or do we point somewhere else? And the answer is we continue to monitor this region. So it turns out that we continue to pick up a large number of detections as we go out beyond 3.5 years. And eventually, we'll sweep up all of the planets in the habitable zone, but we'll still begin to learn more about what's going on with planets that are farther out that have longer periods. And we're interested in understanding the whole architectures of planetary systems. So if we wanted to point somewhere else, we'd have to go through a similar 5-year period of characterizing every star in another field. So that'd be a huge effort. Any other questions? Yes, in the back.
If you had 2 planets of similar size, both orbiting the same planet like us and Venus, can you tell the difference between them? Are they,
Yeah, so the question is, if there are 2 planets of the same size like Venus and the Earth, can we tell them apart? And the answer is yes, we can tell them apart, because they orbit at different periods. So we'll be able to distinguish which one is which as they're transiting by.
Radial velocity or with the transiting?
Well, whatever method you use, whether it's radial velocity or transits, anything that measures the period of the orbit, you'll be able to distinguish between the 2 because they'll have different orbital periods. As one of Kepler's laws relates the orbital period to the size of the orbit. So as you change the size to a smaller and smaller orbit diameter, it moves around the star faster and faster. So you can definitely tell them apart. Yes, in the center. Some in the center.
What, if the budget holds up, probably the next thing to go is going to be whatever propellant or stuff you're using to orient. What's the maximum feet reasonable lifespan of this thing?
So the question is, when do we expect to run out of propellant? What's going to fail on the vehicle? We have one consumable on the vehicle, which is propellant. We have a second consumable on the ground, which is money. But on the vehicle, we have a small amount of propellant. We use the propellant to manage the momentum that builds up from the solar pressure that's exerted on the solar panel. We sized that to last for at least 8 years, or 6 years rather, and it looks, based upon how much we're using, that it'll probably last about 8 years, maybe a little bit longer. So we expect to have a healthy extended mission, at least from the point of view of any consumables, so we'll be able to run the mission well beyond 3.5 years if all goes well. Yes, sir.
Focusing on one section of the sky, is it reasonable to assume that the distribution of habitable planets would be equal in other parts of the galaxy, or more likely in some portions of the galaxy than another?
Well, that's a good question. The question is, can we extend what we learn about this part of the galaxy to the galaxy as a whole? And I think the answer to that is to first order, the answer is yes. We believe that this region of the galaxy is representative. You know, we're only looking at a very small piece of the galaxy, but we believe it's representative of life in the disk of the galaxy. So I think to first order, we will be able to generalize across the entire galaxy from the results we get from Kepler. Yes, ma'am.
Once you've gathered all this library of statistics about planetary architecture, is there any practical application for this information?
Practical applications for this information. Well, I would say I can't think of any practical applications other than understanding our place in the universe and knowing whether there are other places like the Earth puts a spring in my step. I mean, as a human being, I want to know things like that. But the practical applications of what we do actually come from the technology that we develop. You know, everything that we build in NASA is unique. Everything we build pushes the frontier of science and technology. And in a modern economy like we have in the 21st century, I can't think of any more powerful force for economic growth than innovations in science and technology. And that's what we're all about here. So what we do in the space business, you know, eventually finds its way into other things that American industry builds. And who knows where it's going to show up in your everyday life. Are there any other questions? Yes, sir.
Given that you're viewing a star along the elliptic plane of the solar system around that star, and there is an Earth-like planet around it in the habitable zone, what's the probability that you simply miss it, that you don't see it, it gets lost in the noise?
Well, one of the big uncertainties in this mission is how variable in brightness are the stars going to be from other factors. Now, when we built the air budget for Kepler, remember I said we have to be able to measure 20 parts per million sensitivity of light changes, brightness changes. We built a whole air budget, and the single biggest term in the air budget is what's the variability of the star itself? And we had only one data point. There was only one star known at that level of precision, and that was the sun, so we stuck the sun in that box. So we don't know whether the sun is typical or whether the sun is unusually quiet. Maybe the reason that we're all here is because we're orbiting an unusually quiet star. Now, the Europeans, the French, have flown a spacecraft called Corot, which was designed mainly to measure the vibrations of stars. The stars are oscillating, and you can tell a lot about the interior structures of stars from that data. So they have a mission that's designed to do that, but it also allows them to look for transiting planets, and they have found about a half a dozen or so transiting planets. And the data that we're now seeing from that mission, which has been flying for 2 years, is that the sun is an unusually quiet star. So it remains to be seen how difficult it's going to be to find these planets against the noisy background of the natural fluctuations of brightness of the star. So I would say stay tuned. Yes, sir.
Is the Corello using the same field as you are?
Corot is not using the same field. Corot is orbiting the Earth, and so they can only look at a region of the sky for a limited, a few months at a time, and then they have to look somewhere else because the Earth gets in the way and the sun gets in the way. So they can find planets that have, short period orbits that are close to the star. They can't find planets like Earth around stars like the sun. So that's a unique capability of Kepler. But they're not observing in the same region. Yes, sir.
Can the data be used for other analyses like gravitational microlensing and things like that?
There are a lot of applications for the data that Kepler will bring down. For the first time, we're going to have measurements of 100,000 or more stars at levels of precision that are well beyond anything that's been measured so far. And so there's an entire consortium of scientists in Europe that are interested in what's called astroseismology, which is measuring the vibrations of stars themselves. So they're eager to crunch this data and learn a lot more about how stars work. We expect that there are a lot of other effects that you can look for, eclipsing binary stars. We might be able to detect comets. We might be able to detect gravitational lenses. Having 30-minute cadence measuring the brightness fluctuations of things is like taking a movie instead of just taking a single still picture. So there are a lot of things that I expect we're going to find. A lot of them we may not even know how to ask the question today. So I would say there's going to be a treasure trove there of data you can mine for other effects beyond just finding planets. Yes, sir.
The lenses you're going to use, is that going to be visible light or different parts of the light spectrum?
This is done in the visible part of the spectrum, and it's because we don't need to go to a different part of the spectrum. Visible is the most straightforward way to build an instrument. We have the best technologies for that, and it's the least stressing. And to get as fine a resolution image in a telescope, the shorter the wavelength of light you work at, the more compact the images are. So you'd like to work at a shorter wavelength to get better resolution, and so visible is a good, convenient place for us to do our work. Plus, we're principally interested in looking at stars like the sun and looking for planets like the Earth around stars like the sun. And the stars, our sun's temperature is such that the peak in its spectrum, the peak in its brightness occurs in the visible wavelength. That's the reason our eyes are sensitive in the visible. And so the visible is a natural place to look when you're looking at stars like the sun. Yes, sir.
How much data are you going to end up with, and how will you make it available to the scientific community?
We're going to wind up with a large amount of data. I don't know how many terabytes of data we're going to have. And the data is going to be released in increments, yearly increments, and it'll be released through the Space Telescope Science Institute. So you'll be able to go to their webpage and be able to get the data from the release there. Now there will be a time delay since we need to calibrate the data and look for the planets that are contained in that data, and then the data will eventually be released to the larger community. So you'll get the data from Space Telescope. Yes, way in the back corner.
Are the orbits random in space, or do they tend to be parallel to the galactic plane at all?
I believe that the theory is that they're randomly oriented. And so that's the reason that there's only about a 0.5% chance that any planetary orbit alignment will be right for us to be able to see transiting planets. Anything else? Yes.
Continuation to that question, is there any correlation between the plane of the disk of the galaxy and the direction, the plane of the orbiting of planets around stars in the galaxy?
I think the answer to that is that it's random. And I think it has to do with when stars form condensing out of interstellar clouds of dust and gas. The momentum in the cloud and where the disk finalizes, when it materializes, is random. Our solar system ecliptic plane where the planet's orbit is canted by 20-some degrees from the plane of the galaxy. By the radial velocity surveys that we do, we can see that there are planets that are inclined in various orientations. So I believe that there's enough mixing that goes on that the orientation is going to be random. Okay, I think with that, we'll draw the evening to a close.